Here's some practice writing double replacement reactions. There's a description here that says a precipitate of barium carbonate is formed when an aqueous solution of potassium carbonate reacts with aqueous barium chloride. And then we want to write the balanced equation. So they're giving me the reactants. I've got the aqueous solution of potassium carbonate and barium chloride. Okay, so here's what I'm thinking in my head. I'm thinking I gotta find these charges. I'm obsessed with knowing all the charges. So I would start this out as potassium carbonate and barium chloride. Well, I look on my periodic table, potassium is a +1. If there's 2 potassium, that means there's a +2 total charge. So this carbonate is a -2. Or you can look it up on page 98. Carbonate is CO3 -2. Barium is kind of down at the bottom of group 2, so he's a +2. Chlorine is a -1. Okay, so positive switches with positive. So I'm going to switch my potassium and my barium. All right, so all I'm going to do now is switch the ions. So I'm going to bring barium with carbonate and then potassium with chloride. I just made a new combination of ions, so I got to check the charges on the product side. Barium is a +2. Carbonate was a -2. Yes, neutral. Oh my gosh, you've got to be kidding. They're both neutral. +1, -1. Another reason why I like to put the charges down, even on the reactant side, is because I'm going to use them again on the product side anyways. So I know then that I have my reactant formulas written correctly, and then I can use those charges to make sure I get the product formulas correct. Awesome. That's the hardest part of all of this, is to figure out what ions are going to switch positive for positive. And it kind of reminds me of the single replacements in that like charges can switch, whether it's a single replacement or a double replacement. I can't switch the ions in a way that would give me like 2 positives together or 2 negatives together. On the product side, it's still got to be a positive with a negative. Okay, so I just did all the hard work. Now I would balance it. So it looks like there's 2 potassium on the reactant side. So I'm going to need 2 potassium on the product side. I've got 1 carbonate on each side. That group CO3 stays the same, so I can just balance it as one big group. 1 barium, 2 chlorine. What do you know? 2 chlorine. If you get the formulas written correctly, I guarantee the balancing part should be the easiest part. And it almost like slaps you in the face. Like it works out. Oh yeah, I needed 2 chlorine anyways. Perfect. Now the last thing that I usually do is put the phases in, the little phase symbols. Now they did tell me that these were solutions of potassium carbonate and barium chloride. So they are aqueous. They tell me that a precipitate of barium carbonate is formed. A precipitate is a solid. It's a solid that forms from the reaction of solutions. So I would expect some kind of like a cloudy solid that would eventually just kind of drop to the bottom of my beaker. Now, they never mention anything about the potassium chloride, but we did kind of mention at the beginning of this that typically when you have a double replacement, you'll have one product that is an ionic aqueous solution, and the other product is either a solid precipitate, a gas, or maybe something like water. Oh, so if we know that the barium carbonate was my solid precipitate, then the potassium chloride is my aqueous ionic solution. And there we have it. Everything is written correctly. We've got it balanced. We've got the phases in. So that if somebody wasn't able to run this reaction, they might at least kind of know what to expect. Now Now there is another way that I can help you predict some of these phase symbols. You gotta jump ahead a little bit in your book to page 246. Here's another chart that I will give you on any test or quiz. Anytime you need it, I'll give this to you. It's called the solubility chart or solubility rules, and it helps you predict whether something will be aqueous or not. So it doesn't necessarily tell us if it's like solid, liquid, gas, but we use it most often for predicting a solution. And insoluble is going to mean solid. So if something is listed as insoluble, it's going to be a solid. If it's soluble, it's going to be aqueous. That means that, yes, it will dissolve in water. Again, it doesn't help me predict like gases or liquids, a pure liquid, but it does help me predict whether something is a solid, like a precipitate, or whether it will be an aqueous solution. So you got to jump ahead a little bit. And we're not really going to do too much else from this last section of the book, but this chart I think is applicable. And so, for example, they'll say a compound that contains salts of alkali metals and ammonia. Salt is just another word for an ionic compound. So alkali metals are group 1, like lithium, sodium, potassium. If you have any compound that contains lithium, sodium, potassium, it's soluble, which means it's aqueous. Now there might be some exceptions. There are a few lithium compounds that might not dissolve real well, but in general, especially anything with sodium, potassium, they all dissolve. They're all soluble. Nitrates and chlorates are soluble with few exceptions. I can't think of any nitrate that does not dissolve in water. They all do. Sulfates and chlorides are mostly soluble with a few exceptions. So for example, if I had something like sodium sulfate, okay, well I could either look at this as being an alkali metal, and anything with alkali metals are soluble, aqueous, or I could look at it in terms of sulfate to say, all right, sulfates are soluble, aqueous, with a few exceptions: lead, silver, mercury, barium, strontium, and calcium. So then I'd say, oh yeah, like sodium's not on the list, so sodium sulfate is aqueous. Same thing with like copper sulfate. All right, well, most sulfates are soluble. There are about 1, 2, 3, 4, 5, 6 exceptions, but copper's not one of them. So copper sulfate would be aqueous. Now on the flip side, if I did have something like calcium sulfate, most sulfates are soluble, but there are a few exceptions, and calcium is one of them. So calcium sulfate is a solid. It would be insoluble. All of these exceptions mean they're going to be solids. And here, when we see the word soluble, that means aqueous. Oh, okay, I kind of get that. Same thing with chlorides. Most chlorides are soluble. Most chlorides are aqueous. There are just 3 that typically don't. Silver chloride, mercury chloride, and lead chloride are exceptions. So silver chloride would be a solid, but something like copper chloride would be aqueous. And then the last group they have are carbonates, phosphates, chromates, sulfides, and hydroxides are mostly insoluble. So most carbonates, phosphates, chromates, sulfides, and hydroxides do not dissolve, and they would stay a solid. But there are some that do dissolve, and the exception is like the alkali metals and ammonia. So, for example, most carbonates do not dissolve. something like calcium carbonate. Calcium carbonate is a solid. But there are a few carbonates that dissolve. But again, most of them are things like sodium carbonate. Okay, sodium carbonate. Yep, that's an alkali metal. That's group 1. So this one is an exception. It would dissolve. So you can use this chart to predict the phase of your products from a double replacement or even a single replacement. If there was something and you're like, I don't know if that's a solid or if that's aqueous, this chart will help you predict. And realistically, if there's something that's a gas, either they'll tell you like oxygen gas is formed, or you might just know that, well, yeah, oxygen is a gas. So this chart is kind of handy. It's on page 246, and I'll put it on the test as well. All right, so let's try some of these guys. Number 21, write a balanced equation for each reaction. All right, so I like to start with the charges. Potassium +1, hydroxide -1. Hydrogen is a +1, and if I look up PO4, PO4 is phosphate, it is a -3. Or I can kind of just figure it out because there's 3 hydrogen, so that would give me a +3, phosphate must be a -3. Now they're going to give me a little hint in that one of the ions formed is water. But yeah, I think that's actually going to make sense because I'm going to switch potassium and hydrogen. I'll switch the 2 positives so that now hydrogen will come over with hydroxide and potassium will come over with phosphate. So now I've got all my charges and I can just use them now in a different arrangement. Now the +1 hydrogen is with the -1 hydroxide, and that's neutral. +1 potassium is with a -3. So to make that neutral, I'm going to need 3 potassium, or I can crisscross. But the key is I have to be able to write those formulas on the product side so that I know things will balance properly. All right, let's do this now. I think I got my formulas. It is time to balance. Originally there's 1 potassium, but now I have 3 on the product side. So I'm going to add in a 3. That gives me 3 hydroxides. All right, OH, I need 3 of you. Oh, but look at this. I wanted 3 hydrogen anyways. Yeah, now I got my 3 hydrogen. 1 group of phosphate, 1 group of phosphate. We got this. And then finally they're telling me water is formed, and HOH is also known as water. And unless I'm told otherwise, water is a liquid. Now, if one of your products is a solid, liquid, or gas, the other product will be some kind of an ionic solution. And so you could assume then that your potassium phosphate is your ionic solution. Or if you were ever just not sure, check out this chart on page 246. So I have potassium phosphate. Potassium is an alkali metal. It's a group 1 alkali metal. And it says that salts or ionic compounds of alkali metals are soluble. So yep, that would be right. That anything with potassium should be aqueous. Now sometimes, like on this chart, you may or may not find one of the ions you're looking for, but I guarantee at least one of the 2 ions in your product would be on the chart. Like on this one, I do have phosphate on that last group, and it says that phosphates are mostly insoluble, but there are a few that dissolve, and one of the exceptions is ammonia is the alkali metal, something like potassium. So I got that right. I'm feeling good. All right, cool. So at this point, if you're feeling really comfortable, obviously you can just try the other ones and fast forward the video and check your answers. or you can keep it running if you want to hear a little more detail or a full explanation on how to solve a couple more double replacements. All right, so I like to start with the charges. +1, -1. Nitrate will be on the polyatomic chart. NO3 is -1. And so then since there's only one silver, it's got to be a +1. Sodium is a +1 and chlorine is a -1. So I'm like always looking at my periodic table so I can find the charges on my ions. Well, now I'm going to switch the positives. So I'll bring sodium with nitrate and silver with chloride. I check my charges again. I made a new combination of ions, and the charges will always stay the same. So if I looked them up on the reactant side, they're the same on the product side. They're just with a different partner. But check this out. Everybody's +1, -1. So they're all neutral, which then also means that I don't even have to balance this. There's one of everything. So then for the phases, they are telling me that there's a precipitate of silver chloride. So that means this is my solid. Then the other product must be my aqueous ionic solution, sodium nitrate. And you could also find all of that on this chart. Anything with an alkali metal, anything with nitrate is aqueous. Chlorides are usually soluble, but there are a few exceptions, and silver is one of them. It says silver and chlorine are insoluble, meaning they're a solid precipitate. Awesome, that one wasn't bad. All right, let's check C. Calcium is in the group that's always +2, which means hydroxide must be -1, since there are two of them. Hydrogen is a +1. Phosphate is a -3. Oh, this is kind of similar to A, right? It's something with hydroxide reacting with hydrogen phosphate. So I'm going to flip the calcium and the hydrogen. So hydrogen will come over with hydroxide. Oh, there's the water formed. It told me water's formed. HOH is another way of writing water. And now calcium, it's going to come over with phosphate. Okay, so when I make a new combination of ions, I check my charges again. Hydrogen hydroxide's fine, but calcium is a +2 and phosphate is a -3, and that is not neutral. So you could either be a crisscrosser or a balancer, and either way, I'm going to need 3 calcium and 2 groups of phosphate. That'll give me a +6, -6. Or just crisscross the charges, but you got to put the PO4 in parentheses so it doesn't look like you've got 42 oxygen to balance. All right, let's do this now. Calcium 1, calcium 3. Okay, I need 3 calcium. Whoa, okay, so that gave me the 3 calcium, but it also tripled my hydroxide. Originally there were 2, now I've got 6 hydroxides. It feels a little crazy, but all right. Yeah, like here's 6 hydroxides, OH. On my reactant side, I have 3 hydrogen, but now if I think like this is the hydrogen ion, I've got 6 hydrogen on my product side. Ugh, I could do that. I'll put a 2 in there, because then 2 times 3 is 6, and that gives me 2 groups of phosphate. Oh, please. That's what we wanted anyways. I guarantee if your formulas are written correctly, these suckers will balance really slick. Awesome. Last thing I would do is put in my phases. So they're telling me that water is formed, water is a liquid, and then my other product should be the aqueous ionic solution. There she is. All right, let's try the last one. One more. Okay. Iron sulfide. Solid iron sulfide. Well, I think this is going to be a +2 on the iron because the sulfur is a -2. Yep, that looks good. Hydrogen is a +1 and chlorine is a -1. All right, so let's switch the positives. So I'm going to bring iron with chlorine and hydrogen with sulfur. So hydrogen is going to be with sulfur and iron with chlorine. Okay, so we got to check our charges. They'll stay the same, but they're just with a new partner. +1, -2. Oh, I need to fix that one. I'm going to need 2 hydrogen. And then a +2 -1. No, I'm going to need 2 chlorine. Okay, again, that's the worst part. Switching your ions and writing those formulas correctly. Because now the balancing should be a piece of cake. I've got 1 iron on each side. I've got 1 sulfur on each side. Gosh, this is good. Oh, but I've got 2 hydrogen on the product side. So I'm going to put a 2 in there. 2 hydrogen. That not only doubles my hydrogen, but it also doubles my chlorine. Which is great because I wanted 2 chlorine anyway. It's balanced. Now they are giving me a hint that a gas is formed. Well, these things usually form some kind of a solid liquid or gas and an aqueous ionic solution. Well, ionic means metal, non-metal. So if I wasn't sure, I see that iron is my metal. This must be my aqueous ionic solution. Or I could look on that chart on page 246, and it'll tell me that most chlorides are aqueous. There are a few exceptions like silver, lead, and mercury, but iron's not one of the exceptions. So iron with chlorine will stay aqueous, which then means that this H2S is my gas. Hydrogen sulfide. That's the poor gas that smells kind of like rotten eggs. And there you have it. So these double replacements seem like a lot of rules, but at least they all get solved the same way. Be obsessed with charge, switch the positive ions, check your charges again on the product side. That's the hardest part. From there, the balancing should always work out as long as you've got your formulas written correctly.